All right, everyone, grab a seat and welcome to today's Explainer. We are diving into a true physics masterclass today on one of the absolute most fundamental concepts in the universe. We're uncovering the real scientific meaning of acceleration. Now, if you think you already know what this word means from your daily life, well, prepare to have your perspective totally shifted. You see, the way we use certain words in casual conversation often falls kind of woefully short of their actual scientific reality. Physics demands precision. It demands that we look past our human biases and define the universe exactly as it operates. So we're going to strip away all the colloquial baggage of the word acceleration and build it back up from absolute scratch.
So let me just ask you, what actually is acceleration? In our everyday conversations, we usually think it just means mashing your foot down on the gas pedal to speed up, right? We associate it almost exclusively with going faster. Well, in the world of physics, that assumption only tells a tiny fraction of the story. To a physicist, slamming on the brakes at a red light, that's a form of acceleration. Spinning in circles on a playground merry-go-round at the exact same speed, that is also acceleration. I know, it sounds like absolute nonsense the first time you hear it, but by the end of our session today, you'll understand exactly why those statements are scientifically undeniable facts.
Here's our syllabus for today's class. First, the true definition of acceleration. Second, magnitude, or speeding up. Third, direction, which is taking a turn. And finally, calculating acceleration step by step.
Okay, let's jump right into part 1, the definition of acceleration.
For those of you taking notes, here is your textbook definition. Acceleration is formally defined as the change in velocity divided by the change in time. If we write that out as a formula, it looks like this: A equals V minus U, all divided by t. It's super important we know our variables here. U represents the initial velocity of the body, basically where you started. V represents the final velocity, where you ended up. And t, of course, is the time it took to make that change. Now, why is time the denominator here? Well, dividing by time is what turns a simple change in speed into a rate. Think about it. A high-end sports car and a person on a bicycle can both eventually reach a speed of 60 miles per hour, which is roughly 27 meters per second. But the sports car does it in 3 seconds flat, while the cyclist bombing down a massive hill might take 3 whole minutes. Time is the great equalizer that dictates how intense that acceleration actually is. Now, if you only take away one single phrase from today's masterclass, please make it this: acceleration means velocity is changing. I'm actually going to repeat that because it's the fundamental core of everything we're doing today. Acceleration means velocity is changing. Whenever I say the word acceleration in a physics context, it strictly and exclusively means that velocity is changing in some way. It does not just mean going fast. A commercial airliner cruises at 500 miles per hour, but once it reaches that cruising altitude and just stays at that exact speed, its acceleration drops to absolutely zero. If velocity isn't actively changing, you do not have acceleration. Period. Which immediately begs the question, how exactly does velocity change? To answer this, we've got to upgrade our vocabulary a bit. In physics, velocity isn't just a simple number. It's what we call a vector. A vector means it carries 2 distinct pieces of DNA. It has speed, which we call magnitude, and it has an arrow pointing somewhere, which is direction. Because velocity is a vector, it's wondrously versatile. It changes if the magnitude changes. It also changes if the direction changes. Or, naturally, it changes if both the magnitude and the direction change at the exact same time. Think of magnitude and direction as 2 separate dials on a control board. If you turn either dial or both of them, velocity changes, and therefore acceleration is happening. Moving right along to part 2, magnitude, or speeding up.
Picture a driver merging onto a long, straight highway. Let's say this car is moving from point A to point B on the entrance ramp, and the driver checks their speedometer. Their velocity during that stretch is 10 meters per second, heading perfectly north. Now, the driver sees an opening in traffic and decides to merge. The car continues moving from point B to a new point down the highway, point C. During the second stretch, the driver pushes the gas pedal down and their velocity reaches 15 meters per second, still heading straight north.
So the crucial takeaway here is that while the direction remained absolutely identical, heading north the entire time, the magnitude changed. The speed number jumped from 10 meters per second up to 15 meters per second. Because that magnitude shifted, the velocity of the car changed. And as we establish in our golden rule, when velocity changes, the car is indeed accelerating. This is the version of acceleration you're probably most intimately familiar with. When you're in that merging car, this change in magnitude is what physically presses your back firmly into the seat. You can literally feel the g-forces of that mathematical change working on your own body. All right, part 3, direction and taking a turn. Now we get to the really fun part. Imagine another car moving up to an intersection, point P. Its velocity as it approaches point P is 5 meters per second, heading north. But upon reaching point P, the car takes a sharp left turn to head west. Now this driver is remarkably precise. They keep their foot perfectly steady on the pedal, maintaining that exact same 5 meters per second speed as they navigate the turn and move away from the intersection. Just to give you a much larger and honestly pretty surprising example of this exact phenomenon, think about the International Space Station. The ISS orbits the Earth at a constant speed of about 17,500 miles per hour. It doesn't speed up and it doesn't slow down. But because it's orbiting, it's constantly turning around the curvature of the Earth.
Let's look back at our intersection example and think about it like a physicist. The magnitude is exactly the same, 5 meters per second before the turn, 5 meters per second after the turn, but the direction changed from north to west. So, Socratic question for the class, is this car accelerating? The answer is a resounding yes. Changing direction means changing our vector, which means changing velocity. Even if the speed number on your dashboard stays entirely the same, simply turning the steering wheel means you are accelerating. This is exactly why when that car turns west, the passengers feel themselves sliding to the right side of the car. Their bodies have inertia. They naturally want to keep going north. But the car's acceleration west is literally pulling them into a completely new trajectory.
Let's wrap up with part 4, calculating acceleration step by step.
Go ahead and jot this word problem down in your notebooks. A car is sitting totally at rest at point A. It's at a stop sign. The driver hits the gas and the car begins moving toward point B. By the time it's moving towards point B, it has gained a velocity of 12 meters per second. And for context, 12 meters per second is roughly 26 miles per hour, so just a very normal neighborhood driving speed. The total time it took for the car to go from a dead stop to that velocity of 12 meters per second is exactly 3 seconds.
Let's break down our earlier formula into some actionable steps. Step 1. We identify our variables. Our initial velocity u is exactly 0 because the car was completely at rest. Our final velocity v is 12, and our time, t, is 3. Step 2. We plug these numbers directly into our acceleration formula. So a equals v minus u divided by t. That gives us 12 minus 0 all divided by 3. And step 3, we simply solve the arithmetic, 12 divided by 3.
Which brings us to our final mathematical answer, 4. But for what? In physics, a number without a unit is pretty much meaningless. Because we took velocity, which is meters per second, and divided it by time in seconds again, we get our standard SI unit for acceleration, meters per second squared. So our car's acceleration is 4 meters per second squared. Now, what does squared actually mean in plain English? It just means that for every single second that ticks by, the car's speed increases by an additional 4 meters per second. At 1 second, you're going 4 meters per second. At 2 seconds, you're going 8. At 3 seconds, you hit 12. Make sure you never forget that squared unit on your exams.
And that brings us to the end of today's masterclass. But before I let you go, I want to dismiss the class with a quick take-home assignment. The next time you're sitting in a moving car, commuting to school or work, I want you to actively observe the physical laws we just learned. Really pay attention to how your body reacts to the movement. Feel the forces at play. When you get pushed back in your seat or lean firmly to the side during a sharp turn, ask yourself, are you changing magnitude? Are you changing direction? Or are you changing both? And most importantly, how many times a day are you accelerating without ever touching the gas pedal? Class dismissed.